We've had a look at how to solve differential equations. Let's just take a slight look aside to see how does this affect various things that we will see in the MACE courses. So we'll look a little bit at applications, and in this exercise let's take a look at damping, friction. So let's go back to where we had a weight on a spring. We saw the equation. It involved the acceleration, it involved the friction or damping, it involved the restoring force. We had a constant right-hand side, and of course this constant right-hand side, if we use a slightly different definition of the position z, we can make this 0. Let's take a look at this equation. We'll also make this k over m term 1, and we'll take different values of p over m here. This parameter here, let's vary and let's see what happens. We will of course use initial conditions. We'll decide that at the beginning it's at its equilibrium position and it's moving with velocity 1 in whatever units we choose. So we'll solve that equation, and as mentioned, we will vary this parameter here. Let's see what happens. When the parameter is equal to 0, we see that our system undergoes pure oscillations. Each oscillation is like the one before. It reaches a maximum height of 1, a minimum height of -1. It repeats every 2 pi. The first time it comes back to 0 is at pi. So this is in a situation where there is no friction at all. Now, of course, no friction at all is a hypothetical situation, but it's certainly worth looking at when we compare this situation to various others. So let's just put in a little bit of friction. When we put in a little bit of friction, you can see that the oscillations start to decay. It reaches a height of around 0.9, a minimum of about 0.8. We get to about 0.7 here. Each oscillation has a lower amplitude than the one before. Well, that's the kind of thing we would expect. There's friction in our system, the oscillations decrease. We increase this parameter a bit more, say, well, we're up to 0.7 now, and we can see that the oscillations are decreasing that bit more rapidly. After the first oscillation, the second oscillation only gets to a maximum height of a little bit less than 0.1. And by the time we get out to 20, we just can't detect the oscillations at all. There is a hint that the first 0 occurs at a value slightly greater than pi here. We increase it further, this damping parameter, and it would seem here that, yes, by the time we complete the first oscillation, the oscillations are so small that we cannot detect them by eye. The system comes back to 0 at around 4. So it seems to be slowing down in this respect as well. Increasing further, well, when we get up to, say, 2, we can't actually see the height being negative. It's not clear if it is oscillating now. And then when we go to higher values of this friction or damping parameter, say to 3, it just seems that, yes, it goes a little bit positive and then it gradually returns to 0. Perhaps it really is not oscillating at this point. Okay, let's go and just look at some of those cases in a bit more detail. What's going on? What insight do we have into the fact that we can solve the differential equation? So let's look at the case with 0 friction. We've simply got that the second derivative plus the function is 0. We solve the equation, we get sine t. Indeed, it does repeat every 2 pi, comes back to 0 after pi. It's described with constant amplitude oscillations. That's what we saw. And then when we put in a little bit of friction, then we can see, yes, our oscillations are decaying. We have a 0.1 dz by dt. So when we solve, we can see we have this decaying exponential multiplied by sine of 0.998t. Well, this term tells us that, yes, each oscillation is decaying here. It's a slow decay. The fact that this is 0.998t rather than just t tells us it's taking just a little bit longer to get back to its starting position. And if we put in a bit more friction, taking the parameter up to 0.5, you can see that the pattern becomes that bit more established here, more rapidly decaying oscillations. We can still see that there's oscillations going on at about t equals 20. Sine of 0.968t, so it's moved away from sine t, but still strongly decaying oscillations. And up to 1, well, by the time we reach 20, we can't see the oscillations, although there is a hint that it goes underneath here. But it does seem, based on the fact we have 0.866t, it's reaching back to 0 at a time greater than pi. So with the friction parameter equal to 1, we have the oscillations decaying, the period getting slightly longer. If we go up to 1.9, then we can see, well, we seem just to have the one oscillation here, but if we look hard enough, we can perhaps convince ourselves it goes under the axis here, and maybe back over again by here, but it's hard to say. But when we look at the algebraic solution, we can see that, yes, we do have a sine term here, so there will be oscillations, but things are really decaying quite quickly, so any oscillations are small. But just increasing the parameter that little bit further, critical friction, critical damping. Now you can see that the solution has changed from being an exponential multiplied by a sine to being t times an exponential. So really at this point we don't get any oscillation. The system moves out, and then the restoring force takes it back, but friction is slowing it down. We have t multiplied by this exponential. We call this critical friction, critical damping, but it's important to note that although the solution here, mathematically, it seems to have a very different form for 0.9, when we look at the graphs, there's not a massive difference between this graph and this graph here. So it smoothly goes through this critical damping regime, where we have te to the minus t, and if we increase, say, to 2.5, you can now see we've got two exponentials, two decaying exponentials. So no oscillations, well, no oscillations here, no oscillations here. And now it's a case of, yes, it just comes out and then returns back to its equilibrium position and stays there. Now, when we solved for cases like this, we would end up with a complex conjugate pair when we solve the auxiliary equation. Here we end up with a repeated root, and here we end up with two real and distinct roots, giving us two different exponentials here. But you can see those last cases, those last three cases, the graphs do all look really quite similar, and you need to go into quite some detail to see the differences there. If we were to increase further, it would simply not reach such a great height, and again it would return to 0. So that's the effect of friction on an oscillator such as a weight on a spring. We have the case without any damping, it just oscillates indefinitely. We have the case with a little amount of damping, and we have the oscillations are decaying. With slightly stronger damping, at the end we can't detect the oscillations at all. We go up to critical damping, and then beyond critical damping, it just rises a little bit and falls back to its original position.